Hi to everyone, my name is Emanuele Solfiti and I'm a PhD student at NTNU. The work that I will present is a review about mechanical properties of flexible graphite. I will introduce the flexible graphite and its applications. I will talk about its microstructure related with the mechanical properties, especially about compression, tensile, and viscous properties. Finally, I will show the conclusion. Flexible graphite is a partially known material. It's known for its high resilience and strong viscous component. That means that it has a high capability of dissipate the energy. It shows good chemical stability even at 3000 degrees, and it shows a low coefficient of thermal expansion and a low gas permeability. All of these properties allow its application on a large variety of industrial sectors, such as in sealing and gasketing. It can be used even in supercapacitors or in electrodes for fuel cells and batteries. Due to its conformability, it can be used in insulation or cooling as a thermal interface and as a resistive heating element. In the last few years, its piezoresistive behavior has been studied in order to apply it for sensing applications. To fully understand the relation between microstructure and mechanical properties, it's important to start from the beginning of the manufacturing process. In these pictures, we can see the natural flakes of graphite. They are highly crystalline and they have a very regular shape, which is almost hexagonal. The graphite indeed has this typical crystalline structure made of layers. In the plane of each layers, the carbon are bonded together with strong bondings such as covalent bondings, whereas in the out of plane direction, so in this direction, they are bonded together by means of weak bondings such as van der Waals. This is a typical multi-layer graphite flake. The first step of the manufacturing process is the intercalation. So a chemical substance, is intercalated and then expanded upon heating, and then the flake can expand over 3 times the original thickness, forming this worm-like or accordion-like shaped particles. And the high regularity of the original flake is retained in some way. For example, this is a sort of honeycomb cell. The last step of the process is the compression. So the powder made of worms is compressed without any additive binder and finally is rolled until it reaches the desired thickness and density. The honeycomb cells of the worms during compression are compressed, but it's important to notice that the walls of each cells are formed by multiple layers, about 60 layers, and in each layer there are a lot of defects, a lot of voids, so these layers can slide. Since these layers can slide during the compression, the cells can stretch and flatten. Again, during compression, the worms retain their own identity, and they they form this compressed particle that we will call the deformation units. They are fundamental in the load carrying mechanism. These deformation units interlock among themselves by only mechanical forces. Another important property is the anisotropy. The first type of anisotropy is due to the pressure applied during the compression, because the higher is the pressure applied, and the higher will be the alignment of these deformation units along the bedding plane. So there is a strong anisotropy between the out of plane and in plane direction. The second type of anisotropy is in the plane of the foil, and it's between the perpendicular and parallel to rolling directions. The compression and the recovery are the two most important properties for sealing and gasketing applications. In this picture, we can see that compression decrease together with the increase of density, so more dense material will compress less. The recovery has the opposite behavior. The commercial range of foils goes from 0.7 to 1.4 gram on cubic centimeter, but there is a region here in which there is a good compromise between compression and recovering, and this is the best region for sealing and gasketing applications. This is the compression can be studied even from with nano indentation tests. This is a typical curve of compression. It's not linear, but from the unloading curve, one can extrapolate the elastic modulus in compression. The values found on literature are not that reliable because they are in a wide range and in different for different values of density. The load carrying mechanism in compression is due to the contribution of both bending of the out of plane of the particles that are not aligned with the in plane direction. So this particle tend to bend, and together with the pressure, the internal pressure given by the trapped air. About the tensile properties, it's important to notice that there is a linear relation between the tensile strength and the density. In this range of density, approximately between 0.5 to 1 gram on cubic centimeter, and the same trend is it's visible from between the flake sizes, so the regional natural flake of graphite, and the tensile strength. So the bigger are the flakes, the natural flakes, the higher will be the expansion ratio, and the bigger will be the deformation units, and this is very important for the fracture behavior. This is a typical stress strain curve. It does not show a linear region, and we can see the effect of anisotropy due to rolling. So probably the rolling pre-stress the material, so it cannot reach a very high strain in the direction parallel to rolling. Conversely, in the direction perpendicular to rolling, the strain is over twice. This relation is a typical elastic plus plastic relation, plastic behavior, and it's valid up to a half of the tensile strength. Typical values of the tensile strength are up to 7 megapascal, and the modulus can arrive up to 3 gigapascal. The load carrying mechanism is based on friction forces among the contact points, the asperities of the deformation units, and the crack borns from multiple locations and propagates along the unit's boundaries. About the viscoelasticity, it's important to divide the low frequency load and the high frequency load. About low frequency, the loss factor is being observed to decrease together with the increase of density. The storage modulus and the loss modulus both increase with the solid content, but what is important is that if we normalize the storage modulus, it seems to be not affected by the increase of solid content. So increase the solid content only affects the viscous component of the material. About high frequency, a linear relation seems to be true about in the flexible graphite region of densities here, and this is a linear relation, and it's still the same as in the low frequency, because increasing the porosity means to decrease the density. So increasing the density in this in this direction means to increase the storage modulus. The mechanism of dissipate the energy is based on friction. So the layers can slide both within the cell, both within the cell walls, uh, far from the edges of the singular cell, but this contribution seems to be negligible compared to the contribution of the sliding, so of the friction forces that born here where the multiple walls merge. In conclusion, flexible graphite has a porous microstructure which is based on the so-called deformation units, and these are fundamental for the load-carrying mechanism. And an important property is the anisotropy, especially in the in-plane and out-of-plane direction. And a lot of factors affect the mechanical properties. In this presentation, I showed especially the effects of bulk density and pristine graphite sizes, but also ash contents and exfoliated volume and so on can affect the mechanical properties, and very strongly. Finally, the energy is dissipated by the sliding of merged walls at the edge of each cell. During my review, I noticed that there is a large lack of data about the mechanical properties, especially at high temperature. And even if this material is applied on high temperature, it's used for high temperature applications. The mechanical properties are not well known at that high temperature, so it's difficult to characterize it's difficult to characterize flexible graphite. It's difficult to know flexible graphite thoroughly. So I have finished my presentation. I thanks you all for your attention, and I'm available for your questions. Thank you.